Disk spill is one of the clearest signs that a Spark job is under memory pressure. In simple words, Spark prefers to process data in memory because memory is fast. But when the executor does not have enough memory to hold the working data, Spark starts moving part of that data to local disk. This allows the job to continue, but it also makes the job slower. In this video, we will explain what spill means, the difference between memory spill and disk spill, why disk spill is expensive, why shuffle often causes spill, how to detect it in Spark UI, and how to reduce it. The key idea is simple. Spill is a warning sign that Spark is running out of working memory. Spill means Spark cannot keep all working data in executor memory. When data arrives, Spark tries to use executor memory to process partitions, shuffle blocks, joins, aggregations, and intermediate results. But if memory fills up, Spark needs to free space so the task can continue. To do that, Spark writes part of the excess data to a slower area, usually local disk. This is automatic, and it helps prevent the job from failing immediately. However, spill is not the root problem. Spill is usually a symptom of memory pressure. If you see frequent spill, it means the workload is asking Spark to process more data than memory can comfortably handle. Memory spill and disk spill are related, but they are not the same level of pain. Memory spill means Spark is moving intermediate data out of faster in-memory structures because execution memory is under pressure. It is a warning that Spark is starting to struggle. Disk spill is more expensive because spilled data is written to local disk and later read back. That extra write and read creates latency, disk input and output, and longer stage duration. So, memory spill is a warning. Disk spill is usually a stronger performance penalty. If disk spill grows, stage time often grows too. Disk spill is expensive because disk is much slower than memory. Data that could normally stay in RAM must be written to local disk, then read back later before processing can continue. Every extra write and read adds delay. This creates more input and output operations, more waiting time, and longer stage duration. In Spark, this usually appears as slower tasks, longer stages, more waiting, and reduced throughput. Even if the job finishes successfully, it may cost more because the cluster runs longer. That is why disk spill should not be ignored. Every extra write and read adds delay, and enough delay becomes a serious performance bottleneck. Shuffle and spill often appear together. Shuffle moves data across the cluster so records with the same key can be processed together. During shuffle, Spark creates intermediate data, sends data between executors, sorts or aggregates records, and prepares data for the next stage. All of this requires memory. If the shuffle is large, if partitions are uneven, or if joins and aggregations create big intermediate results, executor memory can fill up quickly. When memory pressure becomes too high, Spark spills data to disk. This is why heavy shuffle stages are often the same stages where you see high memory spill, high disk spill, and long-running tasks. Heavy shuffle and spill are a dangerous combination. The best way to detect spill is to use Spark UI and check the metrics. Start with the stages that have high duration or low throughput. Then look for memory spill and disk spill values. If memory spill is high, Spark is struggling to keep working data in memory. If disk spill is high, Spark is writing a lot of data to local disk, which usually hurts performance more. Also check shuffle read, shuffle write, fetch wait time, and long tasks. One high metric is a clue. But spill plus long tasks plus heavy shuffle is much stronger evidence that memory pressure is affecting your job. Use metrics, not guesses. Memory pressure is usually caused by the shape of the workload, not just one setting. Large shuffles can move huge amounts of data between tasks and executors. Big joins can multiply data in memory, especially when tables are wide or not filtered early. Large aggregations can build big in-memory states and hash maps. Poor partition sizing can create huge tasks if there are too few partitions, or too much overhead if there are too many tiny partitions. Caching too much data can consume memory that Spark needs for execution. Skewed data creates hotspots where a few tasks use much more memory than the rest. Insufficient executor memory or wrong cluster sizing can make all of these problems worse. To reduce spill, shrink the workload before scaling the cluster. First, partition better. Use keys that distribute data more evenly and reduce skew. Second, filter early. Remove unnecessary rows as soon as possible. Third, reduce columns early. Wide data uses more memory, so select only what you need. Fourth, pre-aggregate when possible. Shrink the data before joins or further processing. Fifth, choose the right join strategy. Broadcast small tables when appropriate and avoid unnecessary shuffle joins. Sixth, avoid unnecessary repartitioning, because extra repartitioning can create extra shuffle and spill risk. Seventh, cache carefully. Cache only data that is reused and fits in memory. Finally, use the right cluster size. Less data moved and less data kept in memory usually means less spill. Let us recap the disk spill diagnostic workflow. First, identify the slow stage using Spark UI. Second, check memory spill and disk spill metrics. Look at spilled bytes and spilled records when available. Third, review shuffle read and shuffle write. Large shuffle volume often explains where the memory pressure comes from. Fourth, inspect long tasks and skew. A few overloaded tasks can cause memory imbalance and spill. Fifth, apply a fix such as better partitioning, a better join strategy, early filtering, fewer columns, or adjusted cluster configuration. Finally, validate the result. Confirm that memory spill and disk spill are lower and that stage duration improved. Spill is a warning sign. Use it to guide optimization.